Hello, everyone. Thanks for coming out again this afternoon to hear the second of Brad Wilson's talk. Brad's a PhD student at University College London, so we're happy to have him joining us remotely, because I presume it would be pretty hard for him to attend physically this seminar in Australia. So Brad's going to be talking about the removable singularity theorem for harmonic maps. Thank you, Brad.
Thanks, Tim. All right, yeah, so today we're going to talk about the second part of the second theorem needed to prove the Uhlenbeck compactness theorem, which is this removable singularity theorem. So let's just start off by reviewing some stuff we did last time about harmonic maps. So a harmonic map will always take the domain to be a Riemann surface, like last time. So it's a smooth map into a Riemannian manifold, which is a critical point for this energy functional. So this norm depends on the metrics of sigma and n, and you're just integrating it up. Okay, and this has like a corresponding Euler-Lagrange equation. So if we embed n into Rn, this equation looks like Laplacian f plus this second fundamental form applied to the derivative equals 0. So this will be useful in the analysis. And then the last fact to remember is that if you've got a conformal map, so this is a map which pulls back the metric on one surface to a scalar, to like a function, a positive function multiplied by the other metric. And you've got a harmonic map, then the energy is conformally invariant. So take the energy over one surface, it's equal to the energy over the other surface of the pullback, which is just the composition in this case. So the reason why this works, again, is because in this expression for the energy, you get one factor of this scalar function popping out from the norm and a cancelling factor popping out from the volume form. So the energy becomes conformally invariant. Okay. And what we started to prove last time was this compactness theorem that Sacks-Uhlenbeck proved. So it says roughly that every sequence of harmonic maps with bounded energy has a subsequence converging to a harmonic map, except at certain points where the derivative blows up. So, but they also quantified what happens around these points. So what happens is if you rescale on small disks, the rescaled maps converge to bubbles. So these are harmonic maps from the sphere. And yeah, so this was what we were trying to prove. And oops, okay. One of the things we showed last time was this small energy estimate. So this is this contributes 1/2 of the proof of the compactness theorem. So we showed that there was a uniform energy threshold epsilon and some constants, such that if you've got a harmonic map from the disk with energy smaller than this threshold, then all of the derivatives are bounded by this function here. So they decay like r to the minus k for the kth derivative. And this is only over a slightly smaller disk. Yeah, so what we need to prove now is this second part, which is the removable singularity theorem. So it says that if you've got a map, a harmonic map from the disk minus the point, so the punctured disk, to your Riemannian manifold N, and if it has finite energy, then it extends over the puncture. So let's just go back to the compactness theorem and remember why this was important. So uh, on this. So you've got your Riemann surface, and there's some points where the curvature blows up. So these are the points where the bubbles are forming. And um, the idea is that on, say, your set of points, singular points is S, and then on the set sigma minus S, your harmonic maps Fn converge to some F. A priori, F is only defined on this set here. But because of a removable singularity theorem, you apply it in each neighborhood of these points, and F extends to a harmonic map from the whole surface into N. And then the other place where we used this theorem was to define the bubble maps. So around these points in small disks, you'll have like some sequence of rescaled Fs. I'll just call them F prime, um, which are defined on successively smaller disks around these points. And after rescaling, well, these will converge to a harmonic map from uh, harmonic map from just the disk into n. But actually, I guess it's for disk minus zero. And then you use the removable singularity theorem to fill in this puncture and extend it also to the whole sphere. Okay. Can I clear everything? Just yeah. All right. So this was how we used that. And okay, so now we'll think about how to prove this result. So last time we had this pretty technical argument showing that if you've got a number alpha greater than 1, then if you know you have a L2 alpha bound on df, then f is actually smooth and all of the derivatives are pointwise bounded on some smaller disk. So this was the main ingredient for well, I guess a consequence of the analysis that we used to show the small energy estimate. And roughly the proof went uh, like this. I'll just sketch it quickly. So we showed that an L2 alpha bound implied a L2 beta bound for beta slightly larger than alpha whenever alpha is between 1 and 2. And so this allows us to increase the integrability of df. And then after you pass alpha equals 2, so for 2 less than alpha, you get something else happening. So you get a uniform bound on df pointwise, um, controlled by some stuff times, I guess, um, controlled by this L2 alpha bound. So what this then lets us do is we do this and we get a bound on df, and then to extend it to higher derivatives, we need to use the elliptic inequality and the Sobolev-embedding theorems to bootstrap. And this eventually shows that all of the higher derivatives are smooth and bounded. Okay. But this is a main ingredient for proof, right? Technically, but we've already done it, which is good. So yeah, so then by definition, F is real analytic and it will extend over the puncture because it's given at that point by its Taylor series. Okay. What next? So what we need to do is to show that df is actually inside this L2 alpha for some suitable alpha. And the way we'll do that is to show that df is in O of z to the some number minus some number slightly less than 1. So, and this will imply it. The reason for that is just because of, so there's this fact that 1 on norm of z, I guess to be out, let's use a different number, letter, beta is in, well, this is integrable. So I guess just L1 if and only if what is it? Beta is less than 2 in this case because that's the dimension of our domain. So applying this here, we want df to the 2 alpha to be integrable. But if f is O of norm of z to the minus 1 minus delta, then this is less than or equal to some constant times z to the minus 2 alpha, 1 minus delta. And then we're just asking for 2 alpha, 1 minus delta to be less than 2, which is satisfied when alpha is slightly less than 1 over 1 minus delta, but still greater than 1. Right. So this is the strategy. We show that df is like this. Okay. So let's do that. So let's define, well, okay, so f is defined on the unit disk, say, and we'll define the energy at some radius to just be integrating only up to the disk of radius r. And we'll use this trick a few times in the proof, but what we can do is because we're just trying to fill a singularity and composing with say a dilation of the disk, which is a conformal map, doesn't change the fact that f is harmonic. We can dilate f and have it defined on a slightly larger disk. So I guess we can expand, and after scaling f as well, we can assume that the energy is less than over the disk of radius 3/2 is less than epsilon. And we can choose epsilon as small as we like, but for now we'll just choose it less than this small energy threshold, which we had from the small energy theorem. And we'll need to make it even smaller later. So if we apply this small energy estimate on the disk of radius norm of z on 2 around z, so let me draw a picture quickly. The situation is something like this. You've got z out here inside the ball of radius 1, and then outside of this you've got the ball of radius 3/2. and we're drawing a disk around the Z here. And so we're applying the small energy estimate on this disk to say that the norm of dF is controlled by a constant times this energy over over the disk. And then we've got this vector of Z squared coming in where we've absorbed the half into the constant. Okay. So then because this energy here is less than epsilon, which we assumed, we automatically get that TF is in O of Z minus one, which is almost what we want, but not quite, because we need it in some slightly smaller power of Z inverse. So to do that, we need to control this energy over this disk of this radius. And to do that, we're going to use a differential inequality. So basically, the idea is that it's enough to show that this is controlled by some positive power of the radius. Because if we go back here, that would mean that this is less than or equal to, say, C Z to the possibly some small number, positive number, and then Z minus 2. And then this is Z to the, and then this is controlled by Z to the minus, like, say, like 2, 1 minus K12 or something. And then we have delta equals K12. All right, so this is the idea. We show that E satisfies this inequality. And the way we're going to get that is to prove this differential inequality and then integrate it. So it's more or less clear that the top line follows from the bottom. This is just as you can rewrite the bottom as, say, like d and dr of r to the minus k times e of r being greater than or equal to 0. This is easy to check. And yeah, then you just integrate this. So so you're integrating from r to 1. So really we should have so 1 e of 1 minus r to the minus k e of r greater than or equal to 0, which is the same as this. Okay. So yeah, we are aiming to prove this differential inequality for the energy. All right, so all right, so how we're going to do that is we're first going to make a change of coordinates. So if we use this this map from this unit disk to the cylinder extending infinitely far downwards, given by this, what this does is it sends small neighborhoods around this puncture off to minus infinity, and this boundary here to the boundary at s equals 0. Okay, so we'll use these coordinates from now on, and we can rewrite the energy. So the metric is just the product metric, so the norm squared of the derivative here is just this. And we're integrating over s less than or equal to 0, and from theta equals 0 to 2 pi. Okay. And on the previous slide or two, we defined E of R, and this is what happens when you translate that into the s theta coordinates. So instead of essentially the idea of this is that scaling, like dilation, is replaced by translation. So it's just a bit easier to work with. All right. So if we change the coordinates on our differential inequality, we lose the factor of r here because that's taken care of by the logarithm, and we just need to prove this. So we're looking to find a case so that this is true. And if we do the same, essentially the same trick as before, like we compose f with a conformal map, which in this case is now a translation. We can, because this is, if we could prove this for say s equals 0, then it would be proved for all harmonic maps for s equals 0. So then you just apply the result to these dilated maps, and you get the general inequality. So that's sort of the idea. So we can just reduce it to the case of proving it for s equals 0. So all we need to do is show this. Okay. So let's start by proving a little identity, which we'll need. So we're going to define this thing called a Hopf differential, which is so if f is a harmonic function, this thing is a holomorphic holomorphic 2-0 tensor. And so this dz squared is like dz tensor dz, not dz wedge dz. And if you have a holomorphic vector field, say something like z del z or something, then if you plug this into one of the dz's, then this thing remains holomorphic, and because holomorphic, well, it will now be a holomorphic one form, and then that implies that it's a harmonic one form. So closed and co-closed, which is important. Okay. Now, if you translate into the s theta coordinates for this thing, and you contract with the holomorphic vector field del s, which I think is probably the same as what I've just written, you get this. So just this expression here, which is a harmonic one form. So I guess it's not immediately clear that it's harmonic, but it is based on the previous slide. all of these things take a little bit to prove. Like this changing in the coordinates and stuff would be a bit of a calculation, but I'm just going to skip that. So the the only important fact for us is that this is a harmonic one form. So yeah, so the point is oops, uh, yeah, so the point is we integrate this over theta and calculate the derivative. So if we do that, we can take the derivative inside, and let's just do a bit of a calculation here. So we want to show that this is um, zero. It's not entirely obvious at first glance, but basically the idea is we know that the this one form is closed. Oh, sorry, I should have said ages ago actually. This notation with the subscript s and subscript theta, this means the derivative. So this is df ds. Okay, can't believe I missed that. But yeah, and that might explain if um things were a bit difficult to follow. Okay, so let's just keep going with this. So if we take the exterior derivative of this thing, um, what do we get? So, well, the term with d theta, that cancels because d theta wedge d theta is just zero. So we're just left with the term that looks like derivative with respect to s of norm of fs squared minus norm of f theta squared. And then ds on the end of that, and wedge d theta. So this is yeah, so we know that this coefficient here must be zero. So this thing inside the integral is zero, and we're good. So the point of this is that this this integral here is independent of s. So let's let's see what we get from that. So as we take s to minus infinity, because the energy of f is finite, which was one of the assumptions in the theorem, these derivatives must go to zero because otherwise this couldn't be true, right? And so when we take the limit as s goes to minus infinity, the this this quantity becomes zero, and we because we know that it's constant, we just extrapolate that to every s. So for every s, we have this equality here. All right, so this will come up in the proof a couple of times. It's going to be useful to be able to make these integrals the same. Okay, so let's begin the proof, and it'll become clear why we're doing this in a second. So let's define this capital F as the average of the so this is the energy over like one slice, I guess, of your cylinder. So and then g of s theta equals f of s theta minus this average. So I shouldn't have had theta here. That doesn't depend on theta. So the idea of this is that on each of these slices, g of s has average 0. So I don't really know what I was trying to draw there, but like as opposed to f, where the average could say go to infinity, like you have just this g, which is a nice zero average function, which is always good in analysis because you want to use things like Poincaré's inequality. Okay, and let's do some calculus or um or just algebra, I guess. This function g, yeah, it has mean zero on each circle, and we can expand the inner product like this. So we just get that. And okay, so let's apply this equality. So if we integrate over this portion of the cylinder, so we've got a cylinder here, and big S is there, zero is here. We're going to integrate over all of this all the way down to infinity. If we use integration by parts as well, what we get is this. So we're integrating df squared. So this is the energy over that region I said. And then using the previous equation with involving g, we bring g into the mix. And we also have this term involving the average. Then we use integration by parts. So we get g with the Laplacian plus some boundary terms. And the idea is that as we take the limit as s goes to minus infinity, this boundary term will go to 0 because we said that the derivative fs was tending to 0 as s goes to minus infinity. And the other one stays, but that's all right. Okay, so let's clear this. And yeah, so this is what I just said. In the limit as s goes to minus infinity, this term up here tends to just be energy at the energy over the whole cylinder, which is what we want to get the differential inequality for. And we're left with these three terms on the right-hand side. So we've got this one involving the Laplacian, and this boundary term, and also this involving the average. So we're going to have to bound each of these, and in order to get our differential inequality. So yeah, here's it written out a bit better. So if we remember that the harmonic map equation was this, so the Laplacian is equal to the second fundamental form of the derivatives. So substituting that in, we get this, and there's these two extra terms here, like I said. So we're going to have to bound all of these. Okay, so let's bound J1 first. So this G, which had average 0 on each slice, this satisfies an inequality like this. So on each slice, it's bounded by its derivative in theta direction, the integral of that. And this can be proved pretty easily using Fourier series. Let's just do that, I guess. So very roughly, G on some slice will be given by some sum of like some Fourier coefficients like this, and G prime will be given by something similar. And the idea is to just use Parseval's inequality. So L2 norm of G is integral of sum of Cn squareds. And yeah, and this will just be sum of the n Cn squareds. And because G has average 0 and C0 is the average, C0 equals 0. So that's the important thing. That's why we're using G as the that's why we're using G instead of F. We need to renormalize the average so that this is true. And then in this case, because the n not equal to 0, these terms here control those ones. We get the inequality. Okay. So let's use this inequality, and we're bounding J1, which is this boundary term. So here's J1, and then we use Cauchy-Schwarz, and then we use this Fourier inequality, which we just proved. And then here, so G theta is the derivative of G with respect to theta, and we know that F of S is constant in theta, so this is just equal to F theta. So we're using that here, as well as the AGM inequality. So remember, the F squared was just norm of Fs squared plus F theta squared. So we're using that here. And then, of course, this is just the derivative of the energy at S equals 0. So this is promising because we've got now at least one of the terms on the right-hand side involving the derivative of the energy, which is what we wanted to prove. Because remember, our differential inequality was something like this. Okay. Let's clear this. Okay. So now we need to bound the other terms. So J2 now. We have f of s equals this average again, and we just calculate it. So yeah, basically if we bring this integral inside here, we get the norm squared of fs, and then just substituting that in again, we get this. Then because I guess this is just using Holder's inequality, so we know that the L1 norm of fs squared is going to be less than or equal to the L2 norm of 1 squared and the L2 norm of fs squared, because we're on a compact domain. This is just 2 pi because we're integrating over each slice of the cylinder. So we just get an extra factor of 2 pi out the front there. And now here's where we use that equality we proved. So remember, we proved that using this Hopf differential that you have something like this going on. So because these integrals are the same, we can split this integral up into half of itself plus half of this. which is exactly the same thing. And then we just get the norm of the derivative again. And this is equal to half of the energy at zero, the total energy. Okay. And yeah, so we've got one more term to bound, but before that, let's just consider a special case of harmonic functions. So if you've got this harmonic function f from surface into Rn, the second fundamental form is zero. So all this is saying is that it satisfies the Laplace equation, which is what harmonic functions should satisfy. And then the first term that we had involving the second fundamental form goes away, and you just get a differential inequality like this. So J1 plus J2, which we already bounded, and you get something like that. So this gives you the inequality with k equals 1, but really the analysis we did just then doesn't really matter for J2 because J2 equals 0 since Fs equals 0. And this is just because any function solving this will have 0 mean. Okay. Right. So that was the special case, and now we move on to adding this nonlinear term involving A. So we're gonna have to change K for that. Right. Okay, so down here this is what we want to bound. And the thing inside the integral is this. So we've got this function g, which has average 0 on all of the slices, and the second fundamental form applied to df. Now, by Cauchy-Schwarz and the fact that this second fundamental form is continuous by linear map, we have this inequality here. So there's some constant and norm of g and norm of df squared. So that's fine. And now we use the Sobolev embedding theorem. So this is I guess in some ways slightly stronger, saying something slightly stronger than this Fourier inequality we did before. But basically it gives a pointwise bound on g by the integral of its derivative. So we know that we said before that derivative of g with respect to theta is equal to derivative of f with respect to theta, because the average, like f, doesn't depend on theta. So we get this equality here, and then using the same trick I said before, like with that theorem, we just get this, and this should say df here, I think. All right, so right, and this is less than this small energy constant which we had. So all of the energies we're working with here are less than this small energy constant. Okay, so now now we choose this epsilon slightly smaller than this small energy threshold. So we choose it so small that there's some sigma in this interval, so that the norm of g is less than this here. So this is just so that we can bound this quantity up here by sigma. And that's exactly what we do. So down here we have the term we want to bound and plug this in, and then we have just sigma times the total energy. Okay, and now we're pretty much done, because all we need to do is plug in these bounds. So the total energy of zero is bounded by this sigma E of zero, which we just proved, plus these other terms which we had before. Rearranging, we just get 1 minus 2 sigma here. And because we chose sigma less than 1/2, this setting k equal to this gives us the differential inequality. So yeah, this is the end of the proof of the small energy theorem. And just just uh just to recap, we were wanting to prove this so that we could get a bound on like how fast the energy decays with the radius, which implies that the norm of df is inside this suitable Sobolev space L2 alpha for some alpha greater than 1. Then we apply the analysis of the previous talk to show that f is real analytic and extends over the punctured disk. Okay, I think that's it.
Excellent. Thanks for taking us through all these estimates, Brad, and showing us how you can remove some of these singularities. Thank you.
Yeah, nice.
Does anyone have any comments about Brad's talk or any questions about his talk or the techniques of his proof? How did you find working through all of these estimates?
Uh, it was pretty I don't know. Some of them were fine, and some of them weren't very easy to figure out what was going on. I
So
think,
do you think you're exposed to different maths, different techniques you hadn't seen before?
yeah, definitely, yeah. All of this, like it's interesting because the conformal invariance plays like a really big role somehow, but it's sort of difficult to put my finger on exactly what it's doing. I mean, obviously it lets you like do all these rescaling arguments and stuff, but and this gets you lots of cool stuff, but maybe fundamentally still I don't understand quite
Oh, well, I
why
guess
it's so
this is not
so
really an answer
interesting.
to your question, but I suppose that
Yeah.
whenever you've got things as strong as conformal invariance, you certainly want to use that as much as you can.
Well, yeah, of course, yeah. Yeah.
Hi, Brad. Do you
Hey,
know
yeah,
how much Sacks-Uhlenbeck paper differs from Donaldson's survey? Like
yeah.
the survey looks tractable and doable, but I was trying to read the paper.
Yeah.
Um,
So I was using both as a resource for this,
yeah.
although mostly Donaldson's one, at least for this talk. I feel like I got more out of um Uhlenbeck's and Sax's paper for the last talk.
Okay.
But
Yeah.
like if you look at their paper after like at least mostly understanding Donaldson stuff, like it's sort of clear that they're using the same sort of ideas.
Mm-hmm.
Like
Okay.
this like I mean Donaldson does stuff quite like slightly differently. For example, he didn't make this change of coordinates here. Uhlenbeck just left it in terms of radius,
Yeah.
which is fine. And Yeah, but I think apart from that, it's like the same idea. Maybe Uhlenbeck didn't explicitly mention the Hopf differential, but implicitly it's
Right.
used.
Okay.
But I guess Donaldson just sort of linked that to some other theory which I didn't really talk about. But yeah,
All right. Thank you.
no worries.
Are there any
Any other
further
questions?
questions for Brad? In that case, let's thank our speaker again for this talk and for his previous talk. Thank you, Brad.
Thanks.
All right, that'll do it for us. I'll stop recording now. Thanks all for coming, and hopefully we'll see you next time.